Welcome to the lecture 13 of Fundamental of Electronics. We will be discussing on oscillators, the principle and the applications. The topics that we are going to cover is on the oscillator, the introduction, feedback oscillators, the oscillators with RC feedback, oscillators with LC feedback, the relaxation oscillators, the IC 555 timer as an oscillator. Oscillator is basically a circuit that will generate a periodic waveform using only a DC supply voltage as the input. So this is the oscillator, and the input that we give is basically DC supply voltage. So the output that we get is basically the periodic waveforms. Periodic waveforms are those waveforms which repeat with respect to time t. Now, these input signal may be repetitive or not repetitive, but generally we do not use any repetitive input signal because we are basically using the DC supply voltage, except for some cases where the synchronization is required for certain applications. The output that we get from the oscillator is basically either in the form of sinusoidal, which is the sine wave, or non-sinusoidal, example the square wave, sawtooth wave, and so on. So here we can see the output that we get it from the oscillator is basically periodic in nature. They are of different shapes, either in the form of sine wave or non-sine wave. And two major types of oscillators are there. The one is basically known as the feedback oscillator, and the second one is known as the relaxation oscillator. We will discuss this in detail. What's the difference between the feedback and the relaxation oscillator? So feedback oscillator basically utilize the positive feedback to return a fraction of the output voltage to the input. We have discussed in operational amplifier about the positive feedback and the negative feedback circuit. So feedback oscillators are using the positive feedback in the op-amp, and the loop gain is basically 1 to ensure that no net phase shifting is there. And the second type of oscillator is basically the relaxation oscillator. It uses RC timing circuit combined with certain switching device. For example, Smith trigger that we have discussed in the previous lecture. This will generate non-sinusoidal waveform typically in the form of square waves. So relaxation oscillators will generate the non-sine waveform. Here you can see the basic elements of a feedback oscillator. The output voltage, a fraction of that is given as the feedback, so it may have attenuation and phase shifting, and it is given to the input of the operational amplifier, which can be the positive feedback or using a RC timing circuit. Feedback oscillators are based on the positive feedback input signal. So a portion of the output is basically feedback in phase to reinforce the signal. So output and input are in phase. It consists of an amplifier, usually in the form of a transistor or op-amp, and a feedback circuit that provide the phase shifting and the attenuation. So the conditions which are required for oscillations are the phase shifting around the feedback loop must be 0 degree and the closed loop gain must be equal to 1. So here we can see the positive feedback circuit. You can have amplifier in the form of transistor or op-amp. The output is fed back through a feedback circuit to the input using the phase shifting or attenuation and to get the oscillations. So two circuits are being shown. In the first circuit, if you see, the output and the input which is given as the feedback are both in phase with each other. Whereas in the second circuit, the output and input are not in phase with each other. The startup conditions, which are the initial condition for oscillation, you require the loop gain, which is AB into B, must be greater than unity to build up the output amplitude. Once the oscillation begins, the gain reduces to 1 to sustain stable oscillation without any distortion. The initial feedback signal typically originates from noise or power supply transient. So here you have the amplifier, the feedback is given. So what we get from the time t0 to a particular time t, where you have the gain greater than 1, you will be having certain oscillations. And then your gain, when it becomes unity, then you have a sine wave. So the initial feedback signal which is generating from the noise or power supply transient will result in certain oscillations. RC feedback oscillators are used for frequencies up to 1 megahertz. The basic common type of the RC feedback oscillators which are going to discuss are the Wien bridge oscillator, the phase shifting oscillator, and the twin T oscillator. RC feedback oscillators will produce the sinusoidal output using the RC circuit in the feedback loop. So, we will be using the RC circuit in the feedback loop to get the sinusoidal output up to a frequency of 1 megahertz. Let us see the first one, which is the Wien bridge oscillator. It will be generating the sine wave and it uses an operational amplifier in a positive feedback configuration with a lead lag network. Theoretically, this amplifier oscillator was developed by Max Wien in 1891 and then it was implemented practically, which was achieved by William Howlett in 1939. The lead lag circuit, which is the primary requirement of the Wien bridge oscillator, consists of two RC networks. One is the lag portion and another is the lead portion. Here you can see the circuit, which is the RC network circuit, where the resistor combination R1 and C1 will be forming the lag portion and the resistor R2 and C2 will be forming the lead portion. So what happened with the frequency response? At low frequency, the lead circuit will be dominating, and at the high frequency, the lag circuit will be dominating. The circuit peak will be achieved at the resonant frequency with a phase shifting of 0 degree. So if we plot the output voltage with respect to frequency, we will see that the initial frequency up to the resonant frequency, we will be having the lead circuit dominating. And after attenuation, at higher frequency, we will see the lag circuit dominating. Here at the resonant frequency, the attenuation will take place, phase shifting will be 0, and we will get the maximum amplitude of the response. Resonant frequency, where the phase shifting is 0, and if we consider the RC network with the two resistors being equal and the capacitor being equal, then we get the output voltage by input voltage is equal to 1 by 3, which is the gain or the attenuation factor. This is the maximum value of the response at the resonant frequency. Resonant frequency is given by 1 by 2 pi RC, and below the FR, the lead circuit will be the input, and the above the FR, the output will be the lag input. Basic Wien bridge oscillator, which is having a lead lag circuit in the positive feedback loop and a voltage divider in the negative feedback loop. So here you can see the op-amp, where if you see the inverting terminal and non-inverting terminal, the inverting terminal, which is the negative feedback, if you can see, that is given with a voltage divider. So the feedback that we get through the voltage divider at the non-inverting terminal, inverting terminal, and the non-inverting terminal, we are basically having a network which is the lead lag circuit. This can be viewed as a non-inverting amplifier configuration. In the bridge configuration, the op-amp is connected across the lead lag circuit and the voltage divider. So here you can see Wien bridge circuit, which is combining a voltage divider and a lead lag circuit. So we have, this is the voltage divider, and here you have the lead lag circuit, which is combining to form the Wien bridge circuit. The condition for oscillation, again, you have the positive feedback requirement, which is having the phase shifting to be 0 at the resonant frequency, and the gain around loop should be 1. So the closed loop gain must be 3, so that the attenuation factor is 1 by 3. So the closed loop gain is 3 achieved when the resistor R1 is equal to 2R2 in the lead lag circuit. So here you can see the circuit which is having the closed loop gain of 3, and the feedback is given with the lead lag of 1 by 3, positive feedback loop phase shifting to be 0. So the first gain, voltage gain around the loop will be equal to 1. So the loop gain, if you see, it is becoming 1 because 3 and 1 by 3 will cancel out each other. The startup condition initially will need the closed loop gain to be greater than 3 to build up oscillation, and the gain must decrease to 3 to sustain the oscillation. And this is achieved by using the Ginian diode arrangement or junction field effect transistor as the voltage controlled register. So the op-amp whose gain should be greater than 3 in the initial condition, and then the gain should be sustaining to 3 to have the sustained oscillations. So the output signal will build up and stabilization will be achieved. Ginian diode stabilization is a modified voltage divider network with R3 and the feedback in the Ginian. So here you can see this is the feedback part which is additionally included along with the register R1, and this Ginian which appears as open to be higher gain. When the output is reaching the Ginian voltage, the Ginian will conduct and the gain will reduce to 3. So this is a simple but circuit but can cause distortion. So this is the circuit with having Ginian diode stabilization, which is that having in the feedback loop 2 Ginian diodes are connected back to back in parallel with the resistor R3. JFET stabilization circuit is a better method using the JFET as voltage controlled register. JFET is operating in the ohmic region. Gate voltage control the drain source resistance, and negative feedback will automatically adjust the gain, and it produce excellent sinusoidal waveform. So this is your op-amp, and we are having the junction field effect transistor here in as a voltage controlled register. So it will be operating in the ohmic region, and these will produce sinusoidal waveform which is excellent in the form of stabilization. Phase shifting oscillators are another type which is having 3 RC sections, each providing up to 90-degree phase shifting. So total you'll get 180 degree. The op-amp inversion provides additional 180 degree for 0 net phase shifting. So this is your op-amp, and you are basically having the 3 RC combination here in the feedback circuit. So this will introduce around 180 degree phase shifting, and the other 180 degree phase shifting will be introduced by the op-amp. So the net phase shifting will be 0. Generally for this circuit, the attenuation factor will be 1 by 29, and that will be required. The amplifier gain should be greater than 29 for the oscillation. The resonant frequency for this circuit comes to be 1 by 25 under root 6 RC. Twin T oscillator is another form which uses 2 T-type RC filter, the combination of low pass and high pass, and this form a band stop response. So here you can see that this is a T network combination of resistor and capacitor. This is also a T network combination of resistor and capacitor. The first one is basically the low pass filter, and the other one is the high pass filter, which is connected with the op-amp. So that is the reason this is known as twin T oscillator. This oscillator oscillates at the center frequency. So we have the center frequency where the negative feedback is minimal, and the positive feedback through a voltage divider we are giving to enable the oscillation. So the positive feedback is given through the voltage divider in the twin T oscillator, and the filter response, if you can see, we are getting at resonance frequency, the center part. Now we'll discuss the LC feedback oscillators, which is suitable for frequencies above 1 MHz. Earlier the RC feedback was suitable be up to 1 MHz, but if you required above 1 MHz, you need to go with the LC feedback circuit. It uses discrete transistors, whether in the form of BJT or APT, due to op-amp frequency limitations. Some of these LC feedback circuit we will discuss, like the Colpitts oscillator, Clap oscillator, Hartley oscillator, Armstrong, and crystal controlled oscillators. Let us discuss the first one, that is the Colpitts oscillators. It uses LC tank circuit with capacitor C1 and C2, and there is an inductor L. So if you can see, there is a feedback circuit which is in the form of LC given in the circuit to form the Colpitts oscillator. The resonant frequency that you get is basically 1 by 2 pi under root L, and the total equivalent capacitor forming the C1 and C2. The attenuation factor is given by C2 by C1, requiring the voltage gain to be greater than C1 by C2 for the startup oscillation. Loading will reduce the quality factor and it will affect the resonant frequency. So this is our amplifier, and in this amplifier the feedback that we give is basically in the form of LC network, and that is known as the Colpitts oscillator, and the circuit is shown for the BJT amplifier. Second form is the clap oscillator, which is a variation of Colpitts with an additional capacitor C3 in series with the inductor. So here you can see there is a capacitor C3 which is given in series with the inductor L in the feedback circuit. So the net feedback circuit is again in the form of LC. The total capacitance now changed in the form of the orientation, and if the C3 is very less than C1 and C2, we can say that the resonant frequency is 1 by 2 pi under root L C3, which improved the frequency stability. So compared to Colpitts, if you use clap oscillator, it will improve the frequency stability. Hartley oscillator is another form where two series inductors we will be using, L1 and L2, and there is a parallel capacitor C5 along with the inductors. So the total equivalent inductance will be L1 plus L2, and the resonant frequency will be 1 by 2 pi under root LT, that is the net equivalent inductor into capacitor. The attenuation factor is given by L1 by L2, requiring the voltage gain to be greater than L2 by L1 for the startup. So this is the Hartley oscillator. The amplifier is formed by the BJT, and the feedback circuit is having the two inductors and a parallel capacitor. Armstrong oscillator uses transformer coupling, which is known as the ticker coil, for the feedback. And here you can see this is the feedback circuit where you are having the transformer coupling. So the resonant frequency in this case is given by 1 by 2 pi, the inductance of the primary network, and the capacitor C1, which is connected in parallel with the transformer. These type of oscillator circuit, which is the Armstrong oscillator circuit, is less common because the transformer size and cost is the main limitation. Other form of LC network oscillator is basically the crystal control oscillator, which is using piezoelectric quartz crystal for high stability and the quality factor Q. It is around several thousand. So it operates in series or parallel resonance mode. So either it will be operating in series resonance or parallel resonance. So this is our symbol of the crystal oscillator, and the equivalent circuit is having the combination of LC where two parallel networks are there. One is having a capacitor CP, which is parallel, and another is a series RLC network. So these combinations will form the series and parallel resonance. The fundamental frequency is limited to 20 MHz, and a higher frequency will utilize the overtone mode. So what is overtone? Overtone are roughly integral multiples of the fundamental frequency. So if the fundamental frequency is Fn, then we have to multiply with n to get the overtone. So this is the integer multiples of the fundamental frequency. So here we can see that in the crystal oscillator, we are having a crystal which is in the feedback loop. So this is the feedback loop, and this is the amplifier which is from the BJT. So the feedback loop will have a crystal oscillator along with a capacitor CC. This is the crystal oscillator, and you can use up to 20 MHz as the fundamental frequency. The next form of the oscillator we will discuss the relaxation oscillator, which is basically using the RC timing circuit and a switching device, and these basically produce non-sinusoidal waveform. Earlier, whatever we had discussed, the output was sinusoidal, but now in the relaxation oscillator, we will be getting the non-sinusoidal waveform in the form of triangular, sawtooth, or square. So common type of relaxation oscillator may produce the triangular wave, or the sawtooth, which is a voltage control oscillator, or the square wave oscillator. Let us see the triangular wave oscillator. This is using op-amp in the integrator and comparator with a hysteresis. We have discussed this principle of integrator, comparator, and hysteresis in our discussion with op-amp. So here we have a comparator and integrator op-amp. They are combined, and the output what we get is basically a triangular wave from the integrated circuit, square wave from the comparator. So the comparator output will be the square wave, and the net output that we get is basically in the form of triangular wave. So square wave we are getting from comparator and triangular wave we are getting from integrator. The frequency resonance is 1 by 4 R1C and multiplication with certain constant which is formed due to the register R2 and R3. So these positions of the registers and the values of the registers will define the resonance frequency, and by setting the R2 and R3 values, you can set the upper triggering point and lower triggering point of the response. So upper triggering point and lower triggering point of the voltage you can get for the Vmax, which is for the comparator output with respect to this ratio of the registers R3 and R2. You will be getting then the triangular wave. If you want to get the sawtooth wave, which is the voltage control oscillator, again you will be using a op-amp, integrator and a switch which is in the form of PUT. PUT is programmable unijunction transistor. So here you can see the op-amp is there and a switch is there in the form of PUT, and in this circuit you are basically getting the output in the form of the sawtooth. So whatever the output you are getting in the sawtooth, so initially what will happen is that there is a capacitor C which is connected across the PUT. So this will be charging and the output ramp will begin and the PUT will be off. So the switch is initially off, capacitor is charging, and we are basically having the initial condition. So as the capacitor discharge in the second part, when the capacitor is fully charged and then it is discharged, the PUT will momentarily turn on. So the PUT will control the peak voltage and the triggering the capacitor discharge. So the frequency again in this case we will be getting, which is dependent on the input voltage, the values of the resistors and the capacitor, and the difference of the voltage of the peak voltage and the feedback voltage. So here you have a source which is controlling the switch, that is a VP, and the feedback VF, whatever you get it at the feedback, you are basically controlling the frequency. The square wave oscillator use an op-amp with a RC circuit and a hysteresis. So here you have the op-amp and you are basically using the RC combination for the feedback with the hysteresis, and the capacitor will charge or discharge. So this capacitor will charge or discharge between the feedback voltages, producing a square wave. So when we give the feedback voltage due to the charging of the capacitor and discharging of the capacitor, we are basically getting an output which is in the form of square wave. Now next we will discuss the 555 timer, which is a versatile integrated circuit with basically two comparators, a flip-flop, a discharge transistor and a resistive voltage divider. So you will be seeing here there is a upper comparator, the lower comparator, there is a flip-flop and there is a discharge transistor in the path which is having the voltage divider. So you will be having the resistor as the voltage divider. So this is the 555 timer circuit block diagram symbol, and it is used as a stable multivibrator, which is basically the free running oscillator, or otherwise we say voltage control oscillator. So this is the internal diagram of the 555 timer. It will produce a square wave output. So the output that you will be getting from this 555 timer is basically the square wave, and the resonant frequency is given by this formula, which is depending upon the RC combination of R1, R2 and the C external, which is connected in the circuit. The duty cycle of this square wave will be dependent on the resistor's value, and the diode addition allows a duty cycle below 50%. So you can have control over the duty cycle also with respect to the resistor. So 555 timer, when it is used as a voltage control oscillator, it will be controlling the voltage on the pin 5. So here you have the pin 5 where you are basically controlling the voltage, and it varies the threshold levels, changing the frequency. Frequency decreases with increasing control voltage. So this control voltage, when you increase, the frequency will be decreasing, and can use for phased lock loops for communication receivers. So the square wave that you are getting from the charging or discharging of the capacitor using the control voltage given in the fifth pin of a 555 timer. You can control the frequency with controlling the voltage. We will conclude what we have studied. So oscillators are basically essential for generating the periodic signal, which form important part for communication, digital and the test system. Feedback oscillators use positive feedback and generate the sinusoidal output, whereas the relaxation oscillator produce the non-sinusoidal waveform using RC timing circuit. LC oscillator and crystal control oscillators are used for generating higher frequencies. The 555 timer is a versatile IC used in unstable and VCO, that is a voltage control oscillator applications. So this complete our discussion on oscillators. Our next lecture we will be seeing on the voltage regulators. Thank you for now.